Hey, cat.
Yeah, it like twists slowly too. It's so weird.
It's like the ultimate resistance band, even though it's not. This is the new shape, bro.
We're gonna like break this.
A cyclone separator can be described as tangential air coming from a particular area using a fluid such as air in this diagram, and with it particles will be inserted as well, creating a cyclical motion where the heavier particles will fall towards the bottom and the air will come out at the top. In this basic schematic, we can see the heavier particles are falling while the air is rising up. This is the basic principle underlying a cyclone separator. To my left, we have given data of Q, which can be defined as the flow rate in meters cubed per second. Rho of P, which is the density of the particle, which for activated carbon is 2,250 kilograms per meter cube. We have the density of the fluid, which is given in kilograms per meter cubed as well. We have the viscosity of the fluid, which is air. We have a given length, an estimated length of the cyclone, and the radius of the cyclone. Now you might ask, why are all these measurements important? Well, in this outline schematic of a cyclone depicted here, we have the R, which is the radius, the L, which is the length, and this does not account for the length of the cyclone, but it is the length of the cyclone chassis to where the inlet starts to funnel. Now, this is important because determining the length of that the cyclone needs to drop before the funnel is activated is an important step in the cyclone calculations, as well as knowing the radius of the cyclone. It is also important to note, as described earlier, that the gas will go out while the solids will settle Another way to describe this is an over-the-top view of the cyclone, where we have the radius, which is measured from the center point, denoted as R, center point of the cyclone, to the wall. We have U of R, and we have U, the tangential velocity. It is important that the tangential velocity will always be greater than the U sub R. This proves that the cyclone will be able to settle the particles that are flowing into the process. If not, if U of U sub R is greater than U theta R, then the particles will not be able to settle and instead will be stuck at the upper level of the cyclone, and they will not be able to settle. Bearing this in mind, useful equations provided by Chapter 9 of the textbook have provided us with a way to calculate the pressure drop of the cyclone, which will be described later.
Okay, so for a cyclone, for our project, the main thing we had to calculate was the pressure drop, which is equal to the Euler's number times the particle or the fluid density times the velocity squared over 2. So the easiest variable to solve is v. And for v, all it is 4 times the flow rate over pi times the diameter squared. So next we're going to solve for Euler's number. All Euler's number is relative roughness. So Euler's number equals the square root of 12 over Stokes' flow of 50. Now the next part is to solve for Stokes' flow 50. All Stokes' flow 50 is a ratio of the centrifugal force to the drag force. So the equation for Stokes' flow 50 equals x crit times the density of the particle times the velocity all over 18 times mu times diameter. So next we have to solve for x crit. X crit is the smallest diameter that these particles will be filtered. Anything bigger than this diameter, the particles will be filtered by the cyclone. Anything smaller than this diameter, the particles will not be filtered by the cyclone. So the formula to find the critical diameter is equal to 18 times the viscosity over the density of the particle minus the density of the fluid times u of r, which is the radial velocity. So an example of this is here's an overview of the cyclone. U of r is going this direction over u theta squared, u theta r squared, and all that is the tangential velocity, and that's the velocity that's going this way in the cyclone times the radius. So first we're going to find the radial velocity. All this is using this basic equation of flow rate equals 2 times pi times r times ur times L, length. And with rearranging this equation, because we have the flow rate, we have the radius, and we have the length, we find that u of r equals q over 2 pi L r. So next we'll find u theta r squared. And all this is, it's a little more difficult, but we have to take an integration from 0 to r of u theta r times 2 times pi times the radius times d of r times L, which is going to be equal to the flow rate. And after some calculus, we find that u theta r is going to equal to q over r squared L pi. And lastly, we plug Euler's back into here. We have the density of the fluid and the velocity, and we find that the pressure drop overall is going to be equal to 6.5 pascals.
fire now. Yeah, that's enough to do it.
Oh, what's the inside of that look like?
Okay. Let's see.
That's the yeah.
Okay, I'll lift up, you hold down.
Okay.
Shit ton of graphite in this.
It looks like we've collected a couple of it. And it also kind of blackened the inside.
Yeah, it's all the powder. I knew that was gonna happen. But the rest is just. I mean, this is actually working a lot better than I expected.
Yeah.
Right?
Cool.
I don't know your name,
You know what? I'm happy with
but
this.
you heard my name.
Okay.
Ooh, hit me with the solo.
Jesus.